Welcome to the second video presentation on equilibrium principles. In the first video, we learned about what an equilibrium reaction was and defined the term dynamic equilibrium. We also looked at a reaction rate graph that showed that there can be differing amounts of products and reactants present in an equilibrium mixture. In this video, we will look more closely at the ratio of products to reactants in the equilibrium mixture. We will learn to write an equilibrium expression. We will use it to calculate the value of the equilibrium constant, and we'll use the size of the equilibrium constant to define the relative amounts of products and reactants in the equilibrium mixture. Ultimately, we want to determine a value that represents the ratio of products to reactants in the equilibrium mixture. But to do this, we have to take into account the stoichiometry of the reaction, and then we will have a mathematical way of representing the equilibrium mixture. Essentially, it's just a formula. We call this formula an equilibrium expression. This is then used to determine the ratio of products to reactants, the value of the equilibrium constant, which we define as a capital K. The value of the equilibrium constant K is the ratio of products to reactants in the mixture. In other words, it's just the products divided by the reactants, shown here in this simplified form. The ratio of products to reactants then becomes a fraction, and the value of the fraction K is called the equilibrium constant. Right, how do we get our fraction? So what we need to do is write something called an equilibrium expression. The easiest way to show how to write the equilibrium expression is to use a generic equation like this. So we've got the chemical species A, B, C, and D given here, with the letters W, X, Y, and Z representing the stoichiometric mole ratio numbers given in the balanced equation. So if we have an equation like this, a generic equation, we would write an equilibrium expression like this. Looks complicated? It's not really. A couple of terms. Capital K is called the equilibrium constant. Square brackets with a C inside means the concentration of species C. So whenever you see square brackets around something, it means concentration of. And if it's raised to the power of Y, then that's just an exponent, the concentration of C to the power of Y. So if we have a look, how would we read this? The value of the equilibrium constant is equal to the concentration of C raised to the power of Y. Y is its stoichiometric mole ratio number, multiplied by the concentration of D raised to the power of Z, divided by the concentration of A to the power of W multiplied by the concentration of B to the power of X. We need to be really careful though. We've got two functions on our denominator. They need to be combined. So in your calculator you'll need to use brackets or do this part separately. A couple of things to remember, really important points. So the concentration of a solid or a liquid cannot be changed. So we do not include them in the equilibrium expression. So we ignore them. So if any of our species A, B, C, or D are a solid or a liquid, just ignore them. Pretend they don't even exist. The second common error is to use a plus sign representing addition instead of a multiplied sign here in the equilibrium expression. Now students usually do this because they look up here and they see species C and species D, and there's a plus sign in the middle, so they just take this whole thing and they transpose it down into the equilibrium expression, forgetting to replace the plus with a multiplied. Don't do that. Common mistake. Two things to remember. Don't use solids or liquids. Don't use a plus. So that's how we write equilibrium expressions, and we'll be practicing these in class. Let's look at an example so you can see how it works in an equation. Here in this sample, we will use this equilibrium reaction between sulfur dioxide gas, oxygen gas, and sulfur trioxide gas. This is a key reaction in a process called the contact process, which is used to make sulfuric acid in industry. Okay, so given this equilibrium equation, we would write the equilibrium expression like this. Sulfur trioxide is a product, so it goes on top, raised to the power of 2, divided by the reactants, which is sulfur dioxide raised to the power of 2, multiplied by, remember, don't lose a plus, concentration of oxygen raised to the power of 1, because there is a 1 there, but of course we don't write ones. So this is your equilibrium expression for this reaction. Make sure these brackets are square ones, not round ones. Square ones being concentration of. So that's how we write an equilibrium expression, which we'll be practicing those in class. What if we had some values? This equilibrium expression is now a mathematical formula used to calculate the value of K, the equilibrium constant. So if we know the concentrations of the equilibrium mixture, and we've been given here some values, these have been determined by experiment, we can then calculate the value of K. So these are our concentration values of this, this, and this. So as long as we can transpose that and do a lot of basic maths, you should get something like this. 0.356 squared divided by 0.011 squared multiplied by 0.0098. Remember, there's two functions on the denominator, so we have to do this part separately. You should grab your calculator now, pause the video, and try this multiplication process yourself and see if you get the same answer as me. Pause. Okay, now let's see if you got the same answer as me. I got 106,878. Big number. What does that mean? Let's have a look at that next. But before we do, this number represents a ratio of products to reactants, so there is no unit. We do not put units for values of K, they are ratios, they are not measured quantities. Let's look at an example, a slightly different one. In this example, you've been asked to determine the concentration of hydrogen ions in an equilibrium mixture of 0.1 molar ethanoic acid that has a concentration of ethanoate ions of 0.0025 moles per litre, and you're given the value of K. So from this, we'd write firstly an equilibrium expression, and it would look like this. Ethanoic acid dissociating in equilibrium to ethanoate ions and hydrogen ions. Then we would write an equilibrium expression. Concentration of ethanoate ions multiplied by the concentration of hydrogen ions divided by the concentration of ethanoic acid molecules. Now we've got some values. Put in the values that you know. We've been given the value of the equilibrium constant. We know the concentration of the ethanoate ions and the ethanoic acid molecules. We've been asked to calculate the hydrogen ions. You should pause at this point and see if you can work this answer out yourself. Pause. If you'd done that, you would get something like this. You'd have to use your algebra skills to rearrange the equation, multiply the equilibrium constant by 0.01 divided by 0.0025 to give you the concentration of hydrogen ions as being this. Of course, it's a concentration, so we should have a unit. What's next? The next thing we will look at is how to use the value of the equilibrium constant to describe the relative position of the equilibrium. In other words, does the reaction mixture favour a high amount of products or a high amount of reactants? This can be easy to see using a seesaw. In this first example, the products are in a higher concentration than the reactants, as shown by the bigger box on the seesaw. In order to balance the seesaw and reach equilibrium, the fulcrum needs to be positioned closer to the heavier mass, the products. So, in an equilibrium reaction, the graph would look like this. This reaction has proceeded far to completion. The concentrations of the reactants has fallen low, the concentration of the products has fallen high. If the products are in higher concentration than the reactants, then the reaction has proceeded more towards completion. The equilibrium position is going to be then towards the products. We can then calculate the value of the equilibrium constant using our ratio of products to reactants. And of course, in this one, Since the concentration of the products is greater than the concentration of the reactants, the relative size of K will be a large number. It makes sense. If the products is a big number and the reactants is a small number, big number divided by small number, pretty easy, big number. And of course we define large as being any number bigger than 1,000. We do this to take into account the differences in stoichiometry of different reactants. So large K means lots of products, not many reactants. What about this one? And this reaction has not gone very far towards completion, and the reaction mixture is still mostly reactants and only a small amount of products. What would this look like on a seesaw? Of course it would just be the opposite. Now the reactants is high in concentration and the products is low, so the position of the equilibrium will be towards the reactants. If we take into account our equilibrium expression, of course concentration of the reactants is higher, so if you have a high number on the bottom and a small number on the top, K will come out small. Since the concentration of the products is smaller than the concentration of the reactants, the relative size of K will be a small number. And of course, we define small as being smaller than 0.001, as this accounts for the differences in stoichiometry of reactants. Almost there. Let's see how this applies to two examples to finish off. In the first example, the value of K was a very large number, 106,000. So therefore we say the position of the equilibrium is towards the product. So therefore that means there is a greater concentration of sulfur trioxide in the reaction mixture than sulfur dioxide and oxygen. This equilibrium is lying towards the products. In the second example we used a solution of ethanoic acid. K was a very small number, and 10 to the minus 5. Much smaller than 0.001. So this equilibrium is more towards the reactants. In other words, there is a greater concentration of reactants, which are of course our undissociated ethanoic acid molecules, these things here. There is a greater concentration of these than there is of either of these two, the ethanoate ions or hydrogen ions. So those are our two extremes. Big K means lots of products, small k, lots of reactants. And that's it. In conclusion, in this video we have learnt how to write an equilibrium expression from an equilibrium equation, and you'll need to practice this. How to use the expression to calculate the value of the equilibrium constant K. And lastly, how to use the size of K to describe the relative amounts of reactants and products in the equilibrium mixture. You should now pause the video and write down these three outcomes onto your whisk sheet. Write a summary on what an equilibrium expression and equilibrium constant is and what they can be used for. You may need to rewind back through the video and write down some of the key statements or examples. You can also refer to a chemical reactivity book for some further reading and clarification. Make sure you record any questions you have from this video that you can think of so we can explore these in class as we practice these ideas.